Hey, BC Calc students, this is going to be your day 31 notes. So for day 31, we're talking about transcendental functions and a little bit more with max min. So transcendental functions, what are they? Well, to understand what transcendental functions are, we're going to first take a look at algebraic functions. So these are functions of which this will make sense to you, contain only algebraic symbols and operations. So we have our classic linear, quadratic, polynomial functions, things that would be rational in general. We can even include in our algebraic functions discussion things that are irrational, things that have radicals to them. But if we think about what transcendental functions are things that are non-algebraic operators like sine of the value of x, things like that are exponential, e to the x, and then moving on to logarithmic, things that have ln x. So we will eventually be able to, and this is kind of crazy, approximate the function sine x with an algebraic function. So that's where we're headed when we think about the approximations that we've done with linear approximation, quadratic. We can eventually take some of these functions and approximate them with something that's in that algebraic list up there. But before we get to that, we're going to do a quick review, and it says to sketch the following using transformations. So if we think about numbers 1 and 3, e to the x and ln of x, those are going to be sort of the parent function graphs of what we eventually sketch in numbers 2 and 4, which are some transformed versions of each of those. So for number 1, y equals e to the x. If I were to sketch that, I'm hoping that you remember that e to the x has some key properties to it. Well, first of all, e as a value is approximately 2.718. A lot more to come about that this year, because the way that e is developed is using a limit property. And you'll be, I think, pretty fascinated once we get to the point where we get to the derivative of e to the x. Okay, so if we have that as our base of the exponential, first of all, the y-intercept is definitely at 0, 1. And another important key feature to pay attention to with exponentials of this form is if it's of the form a to the x, we definitely have a horizontal asymptote at y equals 0, so we'll kind of place that appropriately there. And you're going to get a function that looks something like that when sketched. So basing my next graph off of e to the x, which is, again, kind of like the parent function here, there's definitely a couple things that are going to happen in order to transform this graph. So in order, if we make a quick list for ourselves, there are 3 things that will happen to the parent function e to the x. One of them being that the direct thing that's affecting e is this new exponent x minus 2, and that's going to be a shift to the right 2 units. So the exponent up here, that change is going to be a horizontal translation. Next thing that would affect e in order, if we think about like PEMDAS, order of operations here, would be that we're multiplying the outside by 3. That's going to be a vertical stretch by that scale factor, so the y values are going to get tripled. And then finally, the last part of this would be that we have this plus 4 on the outside, and that's going to take the whole graph and shift it up 4 units. So we do have a vertical translation that would take the entire graph, pick it up, and move it up 4 units. So when all is said and done, if we think about where this new graph is going to fall, well, it's definitely not going to fall below the x-axis at all, according to the transformations. So we can move that x-axis down pretty far. If we think about all the shifts that are occurring, the right, the vertical stretch, and the up 4, this asymptote is going to wind up moving up 1, 2, 3, 4 units. Okay, it doesn't really get affected by moving right 2 or the vertical dilation there. But we have y equals 4 as the new horizontal asymptote. And if you want to, like a couple points for accuracy, or even really just one, you can kind of chase around the point 0, 1. And what I mean by that is, where would that fall on the graph if we move it to the right 2, do this vertical stretch, and then up 4? So 0, 1, when I move it to the right 2, would now have an x value of 2. And if I multiply this y value by 3 and then move it up 4, that's going to correspond with the point 2, 7. So right about there. Now again, in terms of accuracy, we know that it's going to have this general shape still according to the transformations. The y value should definitely be growing faster than They are in the parent function, so it's tough to illustrate that maybe without having a specific piece of graph paper to graph over, but the y values get tripled. We definitely move the graph 2 units to the right, and everything gets shifted up 4. So we'll try and be somewhat accurate about that sketch, but maybe with graph paper we'd see some of those changes a little bit more definitively there. Moving on to ln of x, so something that you should be thinking about for the function ln of x is that it's certainly connected to what we have for e to the x, right? Ln, of course, being the natural log of x. When we think about this graph, you really got to be thinking about that this is the inverse of the function e to the x. So this graph flipped over the line y equals x would be the resulting graph for ln of x. So ln of x has an x-intercept at 1, 0. And instead of having a horizontal asymptote at y equals 0, ln of x winds up having a vertical asymptote at x equals 0. So all things that it's been a little while since you've graphed some of these functions, but hopefully they do have a familiar shape to you. And ln of x has very slow growth, okay? It is increasing over its domain, but certainly as compared to e to the x, its inverse function here, logarithmic growth is much slower than exponential growth is. All right, so at this point, maybe you can sketch this without necessarily having me walk you through it. I'd recommend hitting pause real quick, see if you can test yourself on what this graph will look like. So there are 3 things that are happening, okay? If you want to double check before you make your sketch that you have them right, it's left 3. The 2 on the outside is again a vertical stretch. So we're going to double the y, and then we're going to go down 1. Okay. So pretty similar to what we had with the exponential function that we were transforming there. So if we go ahead and draw a set of axes here, and we think about those transformations that are occurring, the only thing that would affect where the vertical asymptote goes is if we have a horizontal translation to the left or to the right. And certainly moving the graph to the left 3 moves my vertical asymptote over to x equals -3. And if we kind of do the same, like where does this point go, 1, 0? Well, it's going to go to left 3. So now it has a x coordinate of -2. And we're going to double this y value and then add 1. So doubling that y value and adding 1, it's just going to be at -2, 1 now. Oops, sorry, we were going down 1. -2, -1. Okay, so based on all that, we're going to have a graph that looks something like this. I probably could have even done a better job to show that vertical stretch, that scale factor of 2. But in the end, we can get a relatively nice rough sketch as to what that graph looks like. Okay. Now, to be honest, at this point where we're at in chapter 4, this is still, the title of chapter 4 at this point in the book is about transcendental functions, but I think it's a little misleading because it seems like we should be then getting into the calculus of some of these functions that are exponential and logarithmic. Certainly we know the calculus of trig functions, but we kind of hold off on that for a little bit. So we're going to keep you in suspense. It doesn't happen actually for quite a while. It's like chapter 7 is when we start learning about some of the calculus behind the derivatives of these functions. But as a really quick aside, just to kind of wrap things up with transcendental functions, in order to apply calculus to certain logarithmic functions, it's good to know how to evaluate something like the log base 3 of 7. And what I'm getting at here is that log base 3 of 7 has the same value as log 7 divided by log 3. So you can use a common log to be able to re-represent log base 3 of 7. Right? When I say common log, I'm talking about log base 10. You could even use natural logs, right? So you can rewrite this in either of these formats because in general, log base b of n is the same thing as log of n divided by log of the base. And again, it doesn't really have to be base 10. It could be natural log, which we know is log base e. Or if you wanted to change the base to any other base, you can make it log base a of n over log base a of B. If there's another base that kind of suits your needs based on the values of B and N, maybe it would make sense to make that change. But moving forward, we're going to see how change of base, this formula here, is actually pretty important in order to be able to apply some calculus to logarithmic functions. Hold off on that for now, okay? But go into the next page. I like this question. This question gives you a function graphed f of x, and it says use the graph of f to estimate the values of c that satisfies the conclusion of the mean value theorem. Oh man, it's been a while since mean value theorem stuck its way. Maybe not that long. You had to do some mean value theorem in the day 28 practice, so I guess not that long ago. But we want to satisfy the mean value theorem over the interval from 0 to 8. Okay, so we probably haven't done this too much when we're given a random graph of f of x. Certainly we know how to justify and verify the conclusions of mean value if we're given the equation for the function. So my only hint for this one before you, of course, try it, would be to think of, we're looking for when does the slope of the secant equal the slope of the tangent? How many points would that happen at over the span of 0 to 8 on this function? And it does say to estimate. So you're not going to necessarily be able to come up with exact values, but do your best to come up with some estimates as to values of C that would satisfy the conditions for mean value. Give me a lot of hints about that one. Hopefully that's enough for you to be able to try that one on your own. We are going to do one more max-min question in the notes, and then that's actually it for today. Just a quick pointers to pay attention to. When you're doing a max-min application, it's really helpful to clean up the expression you're trying to maximize or minimize before trying to take the derivative. So sometimes it's easy enough, like if you're multiplying two expressions together, depending on the scenario, you might be able to multiply the expression out. Maybe it's a quick distributive property so that you don't have to use product rule. Okay, or maybe to avoid chain rule, you might use some techniques to get rid of exponents and things like that. So you might want to clean things up, just as a quick note there. Here's the next one. Due to symmetries that some of the figures have, try maximizing or minimizing just what's happening in the first quadrant. If you do that, just make sure that you actually answer the full question, but you're going to see a lot of questions where we're talking about, areas that we're trying to maximize. And if you just look at the part of the area that's in quadrant 1, maximize or minimize that, and then apply that to however many other quadrants the figure has. If there's symmetry, that might be a good thing to look into. And then if anything's involving distance specifically, instead of maximizing or minimizing a distance, try to max or min the distance squared instead. That's going to be a nicer looking function to apply some maximization techniques with derivatives to, because this will make the algebra for doing the derivative much easier. So just a couple quick notes. I think these will be helpful pointers as you continue to do more max-min practice. We've got one max-min to try. And it says find the exact dimensions of the rectangle of largest area that is inscribed in a semicircle with radius equal to 2. And the hint is to place the center of the semicircle at the origin. So if we take a look at creating a quick sketch of what we got going on here, if we place, according to the hint, the center of the semicircle at the origin, if we have a radius equal to 2, we know that the semicircle is going to look something like that. We'll pretend like that actually hit it, y equals 2. And what we're trying to do is we're inscribing a rectangle underneath it. And we want to determine the largest possible area for this rectangle. And once I know what the largest area is, specifically, actually, what are the exact dimensions that maximize the area? So we'll just make sure that in the end, we're careful that we're answering the correct question. Okay. So there's a couple different approaches here. Like we could think of this as being, because of the symmetry, we can maximize just what we have in the first quadrant and then double that to figure out the total dimensions, right? And figure out what the max area of this figure would be. I don't think it'll be that much more challenging though to think of the area of this entire figure. So no matter what this distance is across the base of the rectangle, no matter what that is, it's going to hit the semicircle at some y value. So the area of the rectangle in general is 2x times y for base times height. However, we need a function that would model what that y value is, because whatever the equation is for this semicircle, whatever x is, the y value is whatever the function is at that point. So what's the equation of a half circle whose radius is 2? Okay. So any point on this graph can be modeled by the square root of 4 minus x squared, right? If you wanted to start with x squared plus y squared equals 4, you can use that as the equation for the whole circle, and then solve for y in this case. Subtract x squared over, square root, square root. We only need the positive radical part because we're only looking at this top half of the circle. Okay. So now that I know that that's y, the area function that we're trying to maximize is 2x times the square root of 4 minus x squared. Now, in terms of defining that area function, the next thing that we might try and do is, find its derivative. And I don't think I'll get to use my pointer in this one necessarily, but it is something to think about. Can we clean up the expression a little bit before trying to max or min? I don't think I can really clean this up too much. I think we're still going to have to use product rule and chain rule at that to find the derivative. So let's go ahead and do that. That the first derivative would be, well, the derivative of the first is 2, right? If we're thinking about product rule, times the second function, square root of 4 minus x squared, plus the derivative of the second times the first function. So it's going to be the first function, 2x, times the derivative of square root 4 minus x squared. So if we use the chain rule here, we're going to bring that exponent of 1/2 out front. So it's 1/2 of 4 minus x squared to the negative 1/2 power. Don't forget to take the derivative of the inside, so times negative 2x. All right, so that's the derivative. We probably want to clean this up a little bit before we start trying to figure out at what values we get a maximum here. So a prime in this case would be 2 square root of 4 minus x squared. Let's see, I could take half of the negative 2, that's negative 1. So x times 2x is going to be negative 2x squared up in the numerator. And then I can bring this back down to the denominator and put it as radical 4 minus x squared. So when this all said and done, the cleaned up version of what that is would be minus 2x squared over radical 4 minus x squared. Okay, so now we want to figure out the critical points so we can just try and determine when is this area function at its maximum. So we can set this equal to 0. And from here, I'm going to add this over to the other side. So if we add 2x squared over radical 4 minus x squared over here, we now want to think about algebraically, how are we going to get x alone? And we actually see this come up a fair bit within max-min applications as far as this algebraic process where you kind of get radicals on opposite ends here. So the nice thing is that they're usually matching each other. So when you multiply both sides by radical 4 minus x squared, you get 2 times the quantity 4 minus x squared equals 2x squared. So distribute the 2 in, 8 minus 2x squared equals 2x squared. Add the 2x squared over to get that 4x squared is equal to 8. Okay, divide the 4 over. I probably didn't have to distribute it over here. I probably could have divided it out to start, but that's okay. So we get x squared equals 2 in this case, and then square root. The critical values to partition around are at plus or minus the square root of 2. Okay, so we need an A prime number line with our critical values. Now we actually have these as critical points as to where the derivative is 0, but there's also values that make the derivative undefined. So for example, negative 2 and 2 would make the derivative undefined, and that kind of makes sense if you look at the fact that this is a semicircle with endpoints at those values at negative 2 and positive 2. So it makes sense that we're not differentiable at negative 2 and 2. So when we're doing the partitioning, it makes sense to have those as endpoints here, but we want to test around negative radical 2 and positive radical 2. And as far as the testing goes, just make sure you're careful when you sub into the derivative up here. If you test 0, that's kind of an easy one to test, right? So testing 0 makes this whole fraction 0 real quickly. And then you get 2 times the square root of 4, which is a positive number. So we're definitely positive in here. And then on, in these other regions, you might have to test, like, just knowing that this is 1.4, test 1.5 or test negative 1.5 out here. And what you'll find is that in each of those cases that we get negatives. So we're going from decreasing to increasing to decreasing. And what we're looking for, as we remind ourselves here, find the exact dimensions of the rectangle of the largest area. So we're looking for a max, and that appears that if we're going from increasing to decreasing, that we have a local max at x equals radical 2. And you know what? I haven't done a great job doing this in the videos, just to kind of save myself some time, but you know what? I'll do a justification. Why not? I feel like I should. It's been a while. All right, so what do we have? Why is x equals radical 2 an example of a local max? So since f prime of radical 2 equals 0, and f prime of x is greater than 0 to the left, and less than 0 to the right of radical 2, we have a local max. Now, this is my justification using the first derivative test. Certainly, we could try the second derivative test. I wouldn't recommend it necessarily because the second derivative wouldn't be maybe the nicest thing to find, given that this is the first derivative. But if you really love taking derivatives, then you could do that and show that at this critical value, the graph is concave down, indicating also a local max. So I've now justified it for you. So just really quickly to finish answering the question, we need the dimensions that maximize this area. So we know that if x equals radical 2, that the base would be 2 radical 2, right? So 2 radical 2 by, what would the height be? Well, if x is radical 2, 4 minus radical 2 squared would be 4 minus 2 under the radical. So 2 radical 2 by radical 2. Those are the dimensions of the rectangle that wind up yielding the largest area, given that semicircle that it is inscribed in. So I like this question. Kind of a nice example of max-min there. So if you have any questions about this one, let me know next time I see you in class. More max-min to come. Have a great rest of your day.